Hi, in this video we are going to talk about red-black trees, so let's get started. Basically the problem is the same as we have seen for the AVL tree. We want to construct a binary search tree from a sorted array. For example, we have 1, 2, 3 and 4 integers. And basically, of course, the root node is going to be the 1. Then we insert 2 to be the right child of 1. Then 3 is greater than 1, it's greater than 2, so it's going to be the right child of 2. 4 is greater than 1, it's greater than 2, it's greater than 3, so it's going to be the right child of 3. What's the problem with it? That we have ended up with a linked list. And most of the operations have linear time complexity as far as linked lists are concerned. And we have seen for binary search trees that we can do better. We can achieve logarithmic time complexity if we construct a tree-like structure. So basically, we have to make sure that the tree is going to be balanced. We can do it with the help of AVL trees. We have been talking about AVL trees, and we can do it with the help of red-black trees. Okay. So the running time of the binary search tree operations depends on the height of the binary search tree. So we should keep the tree balanced in order to get the best performance. In an AVL tree, we have seen that the heights of the two child subtrees of any node differ by at most 1. If it's greater than 1, this difference, then we know for certain that we have to make rotations. Another solution to the problem is the so-called red-black trees. AVL trees are faster than red-black trees because they are more rigidly balanced. We check on every insertion whether the tree is balanced or not, and if it's not balanced, then we make it balanced with the help of rotations. So it is quite counterintuitive that it takes more time to construct an AVL tree. So in this sense, AVL trees are slower than red-black trees. But on the other hand, if we have constructed the AVL trees because they are more balanced than red-black trees, search operations are going to be faster. Okay, so operating systems relies heavily on these kinds of data structures, so they are quite important. And of course, the average case running time is going to be the same as the worst case running time. This is why AVL trees and red-black trees have came to be. The average case running time can reduce to linear time, as we have seen for binary search trees, if we try to construct a binary search tree from a sorted array. Here, for AVL trees and red-black trees, we make sure that the worst case scenario is going to be logarithmic as well. Okay, so what about the red-black properties? We have been discussing AVL trees and we have come to the conclusion that we have to consider the height parameters. And if the height parameters differ as far as the left subtree and the right subtree height parameters are concerned, then we know for certain that we have to make some rotations. Here, we are not going to deal with the height parameters. We have the so-called red-black properties, and if these red-black properties are violated, then we know for certain that we have to make some rotations. So what are these properties? For example, each node is either red or black, hence the name red-black tree. It's very important that the root node is always black, no matter what. All leaves node, it's very important, the nils or the nulls are black. We are going to assign these nils to the null pointers. So we are going to use these nils or nulls to represent that, for example, the given node doesn't have a left child or a right child. So if there's a child missing, we are going to represent it with a nil or a null. Why is it good? Because we assign the color black to these objects, and basically this is how we are able to check whether the red-black properties are violated or not. It is like assigning the height parameter -1 as far as AVL trees are concerned. If you recall, we had to assign -1 to null pointers in AVL trees because this is how we were able to check whether the height parameters are differ more than 1 or not. Here we have to assign these null pointers and we have to assign the color black to these null pointers because this is how we are able to check the red-black properties. So it's very important that these leaves nodes, in the sense that these null pointers are black, so this is represented with color black. And every red node must have 2 black child nodes and no other children. So it means as well that it must have a black parent. So as you can see, every red node has exactly 2 black children. So for example, the node 8 has a left child 1 and the right child 11. Both of them are black. For example, the 19 has 2 children, the 15 and the 25. Both of them are black. And basically this is why we have to assign the color black to these null pointers, because this property is going to be okay. For example, let's consider the 22. Basically, it is a leaf node. It has a null left child and a null right child. But because we assign the color black to null pointers, it's going to be true that basically this red node has 2 black children. Okay, they are null pointers, whatever. So every node must have 2 black child nodes and no other children, and it also means that it must have a black parent. Every path from a given node to any of its descendant null nodes contains the same number of black nodes. For example, let's consider a situation. Let's try to go from the root to the rightmost item. It contains basically 2 black nodes, the 13 and the 25. Let's consider, for example, the leftmost item. It is the 1, and basically the 1 is black and the root node is black. So it is also true that every path from a given node to any of its descendant null nodes contains the same number of black nodes. This is how red-black trees works, okay. Okay, so this is a typical red-black tree. You can check all the red-black properties here, and basically we just have to make sure that the root node is black. We just have to make sure that we assign null pointers if a child is missing, and basically to assign the color black to these null pointers. And basically these are the most important features for red-black trees, okay. What about the rotations? These rotations are exactly the same as we have seen for AVL trees, and it is exactly same as we will see for splay trees. So basically we have a subtree on the left, D, B, E, A, and C. The root node is the D, and we can make a right rotation. And basically this tree is going to be rotated to the right, which means that the root node's left child is going to be the root node after the rotation. And it is true. On the right subtree, we have seen that after the right rotation, the B is going to be the root node, and the B was the left child of the previous tree's root node. Okay. It's very important to know that if we make a right rotation and then left rotation, then we are going to end up with the same tree. Okay, so we can make right rotation, and basically we just have to make a left rotation, which is rotating the whole subtree to the left. So after rotating the tree where the root node is B, we rotate it to the left, then of course we end up with the original tree, so the root node is going to be the D again. So we just have to update the references, which can be done in order 1 constant time complexity, so that's why these rotations are not that expensive. We just have to manipulate the references, and it's very important that these kinds of rotations are not going to change the basic features of the given tree. For example, the minimum item is going to be the same. It's going to be the leftmost item in the tree. The greatest item is going to be the rightmost item in the tree. So let's consider, for example, in the left subtree, the smallest item is the leftmost item. It is the A. What about after the rotation? It's going to be the leftmost item, which is the A again. So we can make sure that the rotation is not going to change the main properties of a given tree. Or for example, the in-order traversal. What's the in-order traversal for the left subtree? It is A, B, C, D, and E. After the rotation, we end up with the tree on the right. What's the in-order traversal for this tree? A, B, C, D, E. So we can make sure that these rotations are not going to change the features of the tree, which is quite good, of course. We don't want to change the properties with the help of these rotations. We just want to use these rotations to make sure that the tree is going to be balanced. It's very important that every new node is red by default. So every node we insert will have the color red. So we keep inserting new nodes in the same way as we have seen for binary search trees or AVL trees. but on every insertion we have to check whether we have violated the red-black properties or not. And if we have violated the red-black properties, we have to rebalance the tree. How? We have two options, whether to make rotations or just to recolor the nodes. And recoloring the nodes are quite easy. We just have to set the color from black to red or from red to black. And basically that's why this coloring phase is going to be very, very fast. As far as the rotations are concerned, the rotations, that's not so expensive too, because we just have to update the references. Anyways, in the next video, we are going to consider the cases when the red-black properties are violated. Okay, thanks for watching.